In this section, we will talk about finding limits using an algebraic method. And later, we will also talk about continuity. So first, let's talk about the theorem on limits of rational functions, which we will be using all the time. Here's what the theorem says. It says, for any rational function f, now remember, a rational function is any function in the form of f of x equals to p of x over q of x. So the rational just refers to a fraction. With a in the domain of f, so this means when you plug in a, f of a exists. The limit as x approaches a of f of x is equal to f of a. So basically, here's what it means. The first thing we should always do to find the limit as x approaches a of f of x is simply plug in a into the function f of x. And if a is in the domain of f, which will happen sometimes, so in other words, if f of a exists and f of x is a rational function, then limit as x approaches a of f of x will simply equal to f of a. Now, when can we use a theorem? When one, f of x is a rational function, and also when x equals a is in the domain of f of x. Okay, so let's take our first example. Evaluate the limit as x approaches 2 of 5x cubed minus 2x. So let's see, is f of x a rational function? Yes. Is x equal a in the domain of f of x? Well, let's find out. Let's plug it in. And plugging in the a value, the 2, into your function should always be your first step. So the limit is going to be 5 times 2 to the third minus 2 times 2. We're plugging in x equals 2 into the x values here. Order of operations, 2 cubed is 8. 2 times 2 is 4. 5 times 8 is 40. And 40 minus 4 is 36. So the limit as x approaches 2 of 5x cubed minus 2x is equal to 36. Okay, next one. Evaluate the limit as x approaches 1 of 4x squared minus 5x times 3x plus 7. Now once again, f of x is a rational function, and let's see if x equals 1 is in the domain. So I'm going to use brackets since I'm going to be using parentheses when I plug in x equals 1. So I have 4 times 1 to the second power minus 5 times 1 times 3 times 1 plus 7. So just as a general rule, always plug in the a value into the x's to see if we get a value that's in the domain of the function. So 1 squared is 1. We get 4 times 1 minus 5 times 1 times 3 times 1 plus 7. 4 times 1 is 4, 5 times 1 is 5, and then 4 minus 5 is negative 1. 3 times 1 is 3, 3 plus 7 is 10. So negative 1 times 10, that's equal to negative 10. So there we go. So limit as x approaches 1 is equal to negative 10. So I'm going to keep repeating this over and over again, but the first step, always plug in your a value to the function to see if we get a value that's in the domain. Okay, now sometimes when we do direct evaluation, which means we plug in the a value, we get this. We get something called the indeterminate form, 0 over 0. If that happens, the limit may still exist, but we need to have some kind of algebraic simplification and or a table or a graph to use to find the limit. So for us to use algebraic simplification, however, we first need to make sure that we have the indeterminate form. Okay, so let's take this example. We want the limit as x approaches negative 3 of x squared minus 9 over x squared plus 3. Okay, so normally our first step is always to plug this in. So if we plug this in, we would get 3 squared minus 9 divided by, negative 3 squared minus 9 divided by negative 3 plus 3. Always use parentheses when you replace a variable with a value. So negative 3 squared, negative times a negative is a positive, so we get 9 minus 9, and then negative 3 plus 3. So this is going to be 0 over 0, which is the indeterminate form. Okay, now once we have an indeterminate form, we should try to simplify this expression. So let's take limit as x approaches -3. The x squared minus 9, let's simplify this into x plus 3 times x minus 3. One thing we can often do is we can factor the numerator and denominator. The x plus 3, that stays the way it is. So if we divide x plus 3 divided by x plus 3, that's 1. So we cancel those, and we're left with limit as x approaches -3 of x minus 3. Now let's plug in -3. So if we plug this in, we got -3 minus 3, which is -6. Now we get a value that's not an indeterminate form. So the limit as x approaches -3 of x squared minus 9 over x plus 3 is equal to -6. Okay, let's try another one. Evaluate the limit as x approaches 1 of t squared minus t over t squared minus 1. The first thing you always have to do is plug it in and check, do I have the indeterminate form? So this gives us limit as x approaches 1. Oh, you know what? Actually, I don't need that when I plug things in, so I'm going to erase it. So I have 1 squared minus 1. T is still 1, so I have 1 squared minus 1. So this is 1 minus 1 over 1 minus 1. Okay, once again, we get 0 equals to 0, which is the indeterminate form. When we have the indeterminate form, let's do some kind of algebraic simplification. So now I'm going to rewrite this as x approaches 1. T squared minus t is, you can factor out a t, which is the greatest common factor. So if I factor that out, I get t times t minus 1. And then t squared minus 1, that's a difference of square, so that's going to be t plus 1 times t minus 1. Okay, so numerator, I factored out a t. Denominator, it's a difference of square, so it's t plus 1, t minus 1. The t minus 1s, they divide to be 1, so we cancel them. So this equals to limit as x approaches 1 of t over t plus 1. Now notice a different notation. If I'm simplifying something, I have to write the limit as x approaches 1 because I'm simplifying the function. But when I plug in the x equals 1 value, then I don't need the limit part anymore. I'm just plugging the x equals 1 into this function. So this equals to 1 over 1 plus 1, which is equal to 1/2. So the limit as x approaches 1 of t squared minus t over t squared minus 1, and that's equal to 1/2. And in class, we're going to go through and graph, maybe not both, but at least one of these functions to show you guys that this is in fact true. Now the next example, this one we will do in class. So you're welcome to work on it by yourself, but we'll go over this one in class. Now here's where it gets kind of a little more complicated. When we have something like this, when you have a square root involved. So first, let's check to see, do we have the indeterminate form? So we have limit as x approaches 0 of square root of 2 times x, which is 0, plus 9 minus 3, all of that divided by 0. Now 2 times 0 is 0, so I can cross that out. So this gives us square root of 9 minus 3 over 0. Radical 9 is 3, so I get 3 minus 3 over 0. That's 0 equal 0 over 0. So we do have the indeterminate form. When we have the indeterminate form, we need to simplify this expression algebraically somehow. But this can't be factored like the other ones could. So when it can't be factored, there's one other trick you can use, especially when you have something involving a square root. We can use something called a conjugate. Okay, here's what a conjugate is. If your expression is a plus b, then the conjugate is going to be a minus b. So if your two terms are a and b, and they're being added, the conjugate is going to be a minus b. The reverse is also true. If you have a minus b, then the conjugate is going to be a plus b. So it's basically the same two terms, but the sign in the middle is going to change. So in this case, your a value is radical 2x plus 9, and your b value is 3, and it's a minus b. So if your original expression is radical 2x plus 9 minus 3, if it's a minus b, then its conjugate is going to be radical 2x plus 9 plus 3. Okay, that's what the conjugate is. Same sign, same terms, different sign. So here's a little trick we can try using. It may or may not work, but let's try it. We have limit as x approaches 0 of radical 2x plus 9 minus 3 all over x. What we can do is we can multiply the numerator and denominator by the conjugate of the numerator. And we always pick the expression that contains a square root. So we multiply by the conjugate of the numerator, which is radical 2x plus 9. That's your A term. Instead of minus 3, it'll be plus 3. That's your B term. And then because this is a new term we're introducing, whatever you multiply the numerator by, you have to multiply the denominator by the exact same thing, which is radical 2x plus 9 plus 3. Because now we're multiplying by a factor of 1. So anytime you introduce a new term, you have to balance it. And the way we balance it is you divide the denominator by the exact same thing. Okay, so now let's do some distribution. So here I'm multiplying a radical 2x plus 9 times a radical 2x plus 9. So I'm going to do that at the bottom here. If I multiply radical 2x plus 9 times radical 2x plus 9, my result is just going to be 2x plus 9. The radical goes away. There's a property we learned in algebra that if you have the square root of a times square root of a, that just equals to a. If you multiply the same expression inside of a square root, the square root goes away. Okay, so radical 2x plus 9 times radical 2x plus 9, this just gives you 2x plus 9. Okay, then we have radical 2x plus 9 times 3. So that's going to be 3 times radical 2x plus 9. And then we have negative 3 times radical 2x plus 9. Oops, sorry. So then this gives us negative 3 radical 2x plus 9. And then finally we have negative 3 times 3, which is negative 9. That's the numerator. Denominator, we have just x multiplied by the whole expression. So it's going to be x times radical 2x plus 9 plus 3. Now on the denominator we can distribute, but we're not going to, and you'll see at the end why not. So for the denominator, just remember to not distribute. So now the 3 radical 2x plus 9 and negative 3 radical 2x plus 9, they're going to add up to be 0 because they're additive inverses. And that's kind of the whole point of the conjugate, to have the middle term cancel, middle term add up to be 0. So here's what we get. We get limit as x approaches 0 of 2x plus 9 minus 9 all over x. Okay, now the 9, because remember the middle term added to be 0. The 9 minus 9, this also adds to be 0. So guess what we get? We're going to get, and I forgot on the denominator, it's not just x, it's x times radical 2x plus 9 plus 3. So guess what happens? On the numerator, we get this. Let's keep happening. So we get limit as x approaches 0 of 2x. So the numerator just simplified to be 2x. And on the denominator, we have x times radical 2x plus 9 plus 3. Now the x and the x, they are going to divide to be 1. That's why I don't distribute the x earlier, because I wanted that x on the outside. So I can just cancel it. So this gives me limit as x approaches 0 of 2 divided by radical 2x plus 9 plus 3. Now I know it's getting kind of messy, and we will go over this in class again, but try to follow along the best you can. Finally, we're going to replace x equals to 0 with the x value. So now let's plug it in and see what happens. When you plug something in, the limit goes away. So we have 2 divided by radical 2 times x, which is now 0, plus 9 plus 3. So 2 times 0 is going to be 0. So we get 2 divided by radical 9 plus 3. Radical 9 is 3, so we get 2 divided by 3 plus 3, which is 2 over 6, which is 1/3. Okay, that was a lot of work. It was kind of messy. And once again, try to follow it the best you can. Because it's so messy, you may not be able to and completely, and that's fine. Just have kind of a general idea. And like I said, we will go over this in class, and we will also go over the next example in class.